All right, get ready to explore because today we're diving deep, and I mean deep, into the world of atoms.
Deeper than usual.
Way deeper. We're going subatomic, looking at the kind of atoms that break down, fuse together.
The atoms that help us understand the age of dinosaur bones, even.
Exactly. It's all about nuclear reactions, radioactive decay.
All those amazing ways we use radiation technology every day without even realizing it, probably.
Oh, absolutely. So if you've got questions about how these tiny invisible processes have massive real-world impacts, well,
You've come to the right place.
we got a lot to unpack, so let's jump right in.
Yeah.
Now, everyone's heard of chemical reactions, right?
Sure, like mixing baking soda and vinegar, that classic volcano science project.
Exactly. But nuclear reactions, those are a different beast altogether. What makes them so unique?
It's the difference between, say, rearranging the furniture in a house versus
Versus completely rebuilding the house from the ground up.
more like transforming the house itself into something totally new. Nuclear reactions involve changes within the nucleus, the very heart of the atom.
We're not just talking about rearranging electrons here.
No, this is the big leagues. We're talking about the potential to change one element into another.
So like the alchemist's dream of turning lead into gold. Is that actually doable with nuclear reactions?
Well, it's not exactly a practical way to get rich.
Okay, so no nuclear jewelry making anytime soon.
But we can, in fact, transmute elements. The real key here is the sheer amount of energy released during these processes.
We're talking orders of magnitude greater than any chemical reaction, right?
You've got it. And this energy is what powers everything from nuclear power plants to, well, the sun itself.
Now that's some serious power. Which brings us to something that's always sounded a bit mysterious to me. Radioactive decay.
It does have a bit of a ring to it, doesn't it?
It always made me think of, like, glowing green rocks in a science fiction movie.
Right, but the truth is, radioactive decay is happening all around us, constantly.
Really? Oh, yeah.
In the simplest terms, it's how an unstable atom tries to become more stable.
So it's like the atom is trying to find a more comfortable state?
Precisely. By shedding excess energy and particles.
And the shedding, that's what we experience as radiation, too.
Exactly. And the type of radiation, whether it's alpha, beta, or gamma radiation, determines how much energy it carries, how far it can travel, all of that.
So each radioactive isotope has a kind of built-in timer for how long this decay process takes.
That's the half-life. It's the time it takes for half of the radioactive atoms in a sample to decay.
Okay, so it's like a clock within the atom itself. And how does knowing this half-life help us, say, date ancient artifacts or even figure out how old the Earth is?
That's the beauty of radiometric dating. Let's say we find an ancient piece of pottery.
Yeah.
By measuring the remaining amount of a specific radioactive isotope in that pottery, like carbon-14,
Right.
we can calculate how long it's been since that material was part of a living thing.
It's like tracing its history back through time.
Exactly. This technique has revolutionized archaeology, geology, our understanding of Earth's history.
That's incredible. But let's zoom in a bit on those different types of radiation you mentioned. Alpha, beta, and gamma. What makes them unique?
Think of them like runners in a race.
Okay, I like this analogy.
Alpha particles, they're big and heavy like shot putters.
So they're the slowest?
The slowest and least penetrating. A sheet of paper can stop them. Then you've got beta particles, much smaller and faster.
Like sprinters.
Exactly. They can penetrate further, but still nothing compared to gamma rays.
Which are like those marathon runners with endless energy.
Pure energy moving at the speed of light. They can even penetrate lead.
So it's all about their energy and how easily they can pass through different materials.
Exactly. And this is why, for example, even though alpha radiation is the least penetrating, it can be dangerous if an alpha emitter gets inside your body.
Because it's releasing all that energy in a very small space.
Right. That's why we're cautious with materials like radon gas, which can be an issue in some homes.
It's all about understanding the risks and benefits. Right. Now, gamma rays, I immediately think of medical imaging, cancer treatment, that kind of thing.
Exactly. Their penetrating power makes them incredibly valuable in medicine. We can create images of internal structures, target tumors with incredible accuracy.
It's like having X-ray vision, but way more powerful.
That's a great way to put it. But of course, we have to handle them with extreme care.
Because that energy, while beneficial, can also be harmful.
Absolutely. It's a balancing act, like so much of nuclear science.
Which reminds me, we hear a lot about nuclear fission and fusion these days. Aren't those the reactions behind nuclear power and even the stars?
You got it. Imagine splitting a heavy atom like uranium into lighter elements.
Wow.
That's fission. And it's what powers most nuclear power plants today.
And it's incredibly powerful because the fission of one atom can trigger more and more fission events, right?
That's the chain reaction. A massive amount of energy is released in the process.
And what about fusion? That's what powers the sun, right? Right. But I feel like we're still trying to figure out how to make it work on Earth.
That's the challenge, isn't it? Fusion involves fusing lighter atoms like hydrogen to form heavier ones.
Yet it releases even more energy than fission.
Way more. But here's the catch. It requires unimaginable temperatures and pressures like what you'd find.
Inside the sun.
Exactly.
So we're essentially trying to create a miniature sun here on Earth.
Essentially, yes. It's a monumental task.
It sounds like it. But the payoff, clean, almost limitless energy, would be huge.
That's what drives so much research in this area. If we can crack the code of fusion,
It would be revolutionary.
no doubt about it. It really does, doesn't it? Creating a star on Earth, the sheer scale of it all.
It's mind-boggling. But fusion power aside, one of the biggest concerns around nuclear technology in general is radioactive waste.
Right, because how do you even begin to deal with something that's dangerous for thousands of years? Millions, even.
Exactly. It's not like we can just bury it and forget about it.
Not quite. It's a multifaceted challenge, that's for sure.
So where do we even start with something like that?
Well, first and foremost, we have to minimize the amount of waste we're creating in the first place, right?
It makes sense. Less waste, less of a problem.
Exactly. So that means optimizing reactor designs, exploring new fuel cycles.
So that they produce less waste, or waste that breaks down faster.
Exactly. Shorter half-lives, less of a long-term burden.
Right. But even with all those improvements, we're still going to have some waste to deal with.
Absolutely. And that's where secure storage comes in.
We've all heard about those deep geological repositories.
Right. Essentially burying the waste deep underground.
But it's got to be more complicated than just finding a deep hole somewhere, right?
Oh, absolutely. We're talking about finding geologically stable formations, places where this waste can be safely isolated for millennia.
So no risk of earthquakes or groundwater contamination?
Exactly. The geology, the hydrology, the long-term stability, it all has to be perfect.
It's a huge responsibility.
Yeah.
Making sure we don't leave future generations to clean up our mess.
It really is. When you're dealing with something as powerful as the atom, the ethical considerations are enormous.
It's that balance again, right?
Yeah.
Harnessing the power while minimizing the risks.
Always. It's not just about what we can do scientifically, but what we should do ethically.
Exactly. Because scientific progress without ethical considerations, that's a dangerous path.
Couldn't agree more. But speaking of doing things with atoms, you mentioned earlier the whole turning lead into gold idea.
Oh, right. Not exactly practical for getting rich, but fascinating nonetheless.
Well, the concept itself, transforming one element into another, that's actually a reality in many fields.
You're talking about nuclear transmutation.
Exactly. And it's crucial in fields like medicine, even astrophysics.
So it's not just science fiction anymore.
Not at all. In nuclear medicine, for example, we use specific isotopes for diagnosis and treatment.
We might have heard of those.
And many of those isotopes are produced through transmutation. It allows us to target specific areas of the body.
So it's like a highly precise tool for medical imaging and treatment.
Precisely. And then on a much grander scale, when we look at the stars,
We're seeing nuclear transmutation in action.
on a cosmic scale, the heavier elements, the ones that make up our planet, even our own bodies.
They were all created inside stars through fusion and transmutation.
Exactly. Pretty amazing, isn't it?
It really puts things into perspective. Okay, let's bring it back down to Earth for a minute, though.
Back to more everyday applications of nuclear science.
Exactly. Like food preservation.
Ah, yes. Food irradiation, always a hot topic.
It is. So how does it actually work? And is it safe? Those are the two big questions I always hear.
For sure. So food irradiation involves exposing food to a controlled dose of radiation.
Usually gamma rays, right?
Right, often from cobalt-60. And this radiation eliminates bacteria, insects, parasites, things that cause spoilage.
So it keeps our food fresh longer.
Exactly. And before you ask, yes, it's perfectly safe.
Because I was going to ask, the food doesn't become radioactive itself?
Nope. The process has been rigorously studied, deemed safe by health organizations worldwide.
That's reassuring to hear. But why even use radiation for this? We've got other methods of preserving food.
True, but irradiation doesn't really alter the taste or texture of the food.
Which is a big plus.
Right. Plus, it can extend shelf life considerably, which is huge for reducing food waste.
So it's good for consumers and for the environment.
You got it. It's a win-win.
It's amazing how nuclear science pops up in so many unexpected places. It's not just about power plants and weapons.
Not at all. It's a surprisingly versatile field. Take archaeology, for example.
Oh, right. Besides radiometric dating, are there other ways nuclear science helps us uncover the past?
Absolutely. There's this fascinating technique called neutron activation analysis.
Okay, what's that one all about?
It's pretty wild, actually. We can bombard an artifact with neutrons,
Okay.
and by analyzing the gamma rays that are emitted, we can figure out its elemental composition in incredible detail.
So we can tell what it's made of, even down to the tiniest trace elements.
Exactly. And that can tell us where the object came from, how it was made, even provide clues about ancient trade routes.
It's like piecing together a historical puzzle, but on an atomic level.
Exactly. It's amazing what these techniques can reveal about the past.
And speaking of exploring, let's shift our focus to the ultimate frontier, space.
Ah, space. Always a popular topic.
Always. But when we talk about space travel, we can't forget about the dangers of space radiation.
Absolutely, those high-energy particles zipping around out there.
A major risk to both astronauts and equipment.
For sure. Which is why shielding is absolutely crucial for spacecraft and spacesuits.
So how do you even begin to design shielding for something as harsh as space?
It's a constant balancing act, finding materials that are both effective at blocking radiation but also lightweight.
Because every pound of weight adds to the cost and complexity of a launch.
Exactly. For example, aluminum, it's great for shielding against low-energy particles, and it's relatively light.
But for those really high-energy cosmic rays, you need something more heavy-duty.
Exactly. And that's where things get really interesting. We're talking about composite materials, layered shielding.
There's even research into using water as a shield, right?
There is. Water is surprisingly good at absorbing radiation.
So like many things in space exploration, it's all about pushing the boundaries of material science and engineering.
Absolutely. And the cool thing is, these advancements in shielding technology, they have applications here on Earth, too.
Right, it's that feedback loop again.
Exactly. What we learn in space often benefits us back home.
It's a win-win. So any specific advancements in radiation shielding that have you particularly excited?
Definitely. One area I'm really interested in is the development of smart materials.
Smart materials.
Yeah, materials that can actually change their properties in response to radiation exposure.
So if the radiation level increases, the material adapts to provide better shielding.
That's the idea. It could revolutionize how we protect astronauts on those long-duration missions.
It sounds like something straight out of a science fiction movie.
It does, doesn't it? But that's the thing about science. What seems impossible today could be commonplace tomorrow.
That's a great point. And it seems like every time we look closer at the world of atoms, we uncover even more possibilities.
It's a testament to how much there still is to learn and discover in this field.
Absolutely. So we've talked about power generation, medical applications, archaeology, space travel. It's incredible how far-reaching the impact of these tiny atoms really is.
It's mind-boggling when you think about it, right? These tiny particles shaping our understanding of the universe, holding the potential to solve some of humanity's biggest challenges.
It makes you wonder what incredible new applications of nuclear science are still out there, just waiting to be discovered.
That's what makes this field so fascinating. The possibilities really do seem endless. There's always something new around the corner, isn't there? Every discovery seems to unlock even more questions.
It's like the deeper we dive, the bigger the ocean gets.
And that's what I find so captivating about nuclear science. It's not just equations and experiments, it's the human element.
Right. It's about how we choose to use this knowledge, responsibly or not.
Exactly. The ethical considerations, they're front and center in this field. After all, we've seen what happens when this technology is misused.
The development of nuclear weapons, that's a stark reminder of the destructive power we're dealing with.
A sobering thought, for sure. Which is why it's not just about what we can do with nuclear science, but what we should do.
It's a heavy responsibility, knowing that these discoveries could be used for good or for ill.
Without a doubt. And finding that balance, it's a challenge that requires a global effort.
International treaties, ethical guidelines, and informed public, it all plays a role.
Absolutely. And it's an ongoing conversation, one that needs to happen at every level, from government agencies to university labs to everyday citizens.
Because at the end of the day, we're all stakeholders in this, aren't we? The future of nuclear science, it affects us all.
It does. And ensuring that this technology is used responsibly, ethically, that's a shared responsibility.
One that we can't afford to ignore. Well, I'd say this deep dive has been a real eye-opener. We've gone from the tiniest atoms to the vastness of space and everywhere in between.
It's been quite a journey, and we've only scratched the surface of what there is to learn about this fascinating field.
It makes you wonder what incredible breakthroughs are just around the corner, what new applications of nuclear science are waiting to be discovered.
That's the beauty of science, isn't it? That sense of wonder, the endless pursuit of knowledge.
And on that note, we'll have to wrap up this deep dive into the world of atoms and radiation. Thanks for joining us for this incredible journey.
It's been a pleasure exploring these fascinating topics with you.
And to our listeners, as always, thank you for tuning in. Until next time, keep those brains buzzing and never stop exploring the world around you.